You kind of missed a lot, Joyce.
Hi, Joyce. No, not that much. Okay, we wrote this down yesterday. Long story short, the error remaining from approximating a function with a Taylor polynomial does equal this expression for some z within these intervals, but since we don't know what the actual function value is, since the whole point of Taylor polynomials was to do what we couldn't do without a calculator, like sine and cosine and e to the x, etc., then there's no way that we can figure out the actual z, so we have to think worst case scenario. And worst case scenario says, okay, fine, since we don't know the actual z, let's just think of the z that will maximize the derivative, because the maximizing the derivative will maximize the error, and we'll know at least the remainder has to be less than that.
Wait, maximize error, don't you want to minimize error?
Well, but if we're trying to make a calculation based on, or to make an allowance based on an error, then we would rather err on the side of what the max is the error could be than what the min is. So we're not actually maximizing or minimizing the error, we're maximizing what the error could be, erring on the side of caution. Anyway, so now we're at an example. From the book, you are going to have a handout, Joyce, but this is from the book to help us out as to how they're going to word things. They say, use the first two terms of the Maclaurin series, therefore we need to put a squiggle because it's going to approximate. We're doing a polynomial of two terms. ln of 1 plus x from the Endeavor card yesterday ends up being x minus x squared over 2, right guys?
Right.
Those are the first two terms. And we're trying to use this at the point, or when x equals 0.1. So we can say ln of who?
1 plus x.
Does that make sense? Plug in when x is 0.1, so ln of 1.1 is approximately 1.1 minus 1.1 squared all over 2. Now technically, if we were to go ahead and solve this, do you guys have your calculators close? Go ahead and close. Let's double check. I'll do it and you do it. We'll see how we did. How are we going to find, first of all, am I right? Why am I writing that entire word?
Yeah.
Cool. Why is alternating series even something that we can do for error?
Because sometimes it alternates.
This series is alternating, right? Which means we can't use the alternating series error bound for all series, just the alternating ones. Okay. Alternating series says that this approximation, 0.495, so s minus 0.495, right, has to be less than who?
1.1 cubed over 2.
Exactly. Because remember, we're doing the next term. So the next term in the progression, the absolute value, well, it's positive anyway. So then what would our actual sum fall between? Wouldn't we take 1.1 cubed
0.66.
divided by 2, which is 0. And wouldn't we add 0.495 on one side? And wouldn't we subtract on the other side? You guys good? Absolute value, one positive, one negative, and we're moving stuff around.
Yeah.
Okay, so from the alternating series bound, we know the error has to fall in between. Once again, we've already brought up the point, not all series are alternating, so therefore we have to have another way of thinking about error with Taylor-Maclaurin polynomials, and we do.
Wait, Miss D.
Yeah.
Is it supposed to be 1.1 cubed divided by 3?
Oh, it is. Thanks, Ken. I was just adding the same thing. This is the next term. Oh, I struggle, so he's wrong.
So it's 0.443666667.
3.
36666. Yeah. And then it's going to be 0.93866.
What's on the other side?
5, 1, 3, 3, 4.
Negative or positive?
Oh, positive. I was looking at the wrong one, making negative.
So that tells us what the error has to be within those values.
Oh no, that's what the sum has to be between. Hold on. What did they actually put in the wording? I'm just solving it like we used to. Find a bound on the error.
The sum has to be
Oh, silliness. We did too much work. But I appreciate it, Amanda.
0.4, 4, 3, that's the answer.
This is the remainder. We can say the second remainder, aka the remainder resulting from the second degree Maclaurin polynomial. What's the notation according to our book? Of x. So of 0.1. They didn't ask us for what the sum falls between on this problem. Usually on the AP they ask you for the sum. They don't care as much about the error as they do the actual sum as well. So we went too far. Thanks for bringing that up, Gerardo. Now that was using the alternating series error remainder theorem, right?
So that is what the error is between?
Yeah.
That's a pretty big gap actually.
Yeah, a bit. But we also used only two terms.
So we don't know what the error actually is, we just know where it falls.
Exactly. Letter B. Now we have to use Lagrange.
I'm not wrong.
I knew you would like that.
I'm like,
Okay, for Lagrange. Here's the dilemma with Lagrange. We'd actually know from our beginning function, which is f of x equals ln of 1 plus x, since we're not just plugging in where we're centered about, which is 0, which is why it's so nice and we can use the special Maclaurin series. We're not plugging in 0, it's f to the n plus first. It's the n plus first term. So we can do things like, we are going to say that the remainder going back to our theorem. The remainder is equal to, and in a way we can say instead less than, it's our worst case scenario. The remainder is going to be less than, and then we're going to go ahead and steal the n plus first x term, the n plus first factorial, but since we're not plugging in for the n plus first derivative, sorry, stuff keeps moving around weird. I don't know. Left. We have to actually find the n plus first derivative ourselves, so that's what we're doing right now. We stopped at the second, right guys? So what derivative do we have to find? The third. So we have 1 over 1 plus x. The nice thing is there's no u prime on this, right? Is that okay? Let me just use r. R is going to be less than the absolute value of, technically the absolute value of 2 over 1 plus z cubed, all over 3 factorial times x cubed. Now wait a minute, hold on. Who do we know x to be? It's r of? 1.1 was the overall, the 1 plus x. What was x by itself? Just 0.1 or 0.1. We could use 2 to say we use second degree Taylor or Maclaurin polynomial. So instead of x, we can actually put in the 0.1 itself, right? I need more space. This is a struggle.
too much stuff, not enough
Can't you
space.
extend base?
I wish. I can't in this
Oh, you
program.
can?
Isn't that a bummer? I could have
We
sworn.
can't extend page.
awkwardly squishy. Okay. So, question, what is my interval? Z must be within what to what?
Negative 0.44366 C to X, right? No.
Is it between 0.9 and 1.1?
Where are we centered at?
0?
So C is 0. Look at your card. C is 0, right? We're centered at 0. And then what's my X? 0.1. So Z has to be between, right? The interval, however it should go, 0 comes first and 0.1 comes second, right? 0 and 0.1. Okay, so as we look at 2 over 1 plus Z quantity cubed, question, if we were to have a calculator, which we have been doing, right? We've been using our calculator on this. This is what the AP would have you using a calculator on. If we were using a calculator, between the values 0 and 0.1, which value is going to maximize 2 over 1 plus Z cubed? Because 0 is going to be a smaller denominator, right? Smaller denominator, bigger number. Oh, can we plug in 0? Yeah. So we're going to say the Z that maximizes such that Z is equal to 0.
What if there's something in between?
Well, what if as in not for this function? But we'll see it. We have more examples.
Like, if
But as soon as you increase from 0 to anything towards 0.1, you're increasing that denominator, right? If you're increasing that denominator, you're lowering that value. Does that make sense? Yeah. You could think of the nature of Z over 1 plus Z cubed for any positive Z's. It's going to be a decreasing function. That might be another way of thinking about it. So we know that our remainder, 0.1, is going to be less than plugging in 0, that's just going to be 1, 2 over 1 is just going to be 2, 2 over, 3 times 2 times 1, 2 over 6 is going to be 1/3. We have 1/3 times 0.1 cubed. 1/10 times 1/10 times 1/10 is 1/1000, right? 1/3 times 1/1000 is 1/1000. It's going to be a point. We got to move this over 3 decimal places, right? Double check me though. 1/3 is 0.333, and then 1/1000. Don't we move it through? 1 and a 2 and a 3. Double check real fast.
3.3 times 10 to the negative 4.
So then move 4 decimal places, and I think you have what I have.
Yes.
Okay. Now, which one seems more precise, the alternating series bound or the Lagrange error bound? Ooh, yeah.
What
a
does
lot
the
more.
Lagrange tell us? Like what the error is?
That we're getting towards, that we're closer.
Now, what I'm trying to see is, do we know for sure it's positive? That's a good question. The error is, I think error is absolute value. Yeah, if you guys look up here, the remainder is the absolute value. Just think like magnitude, it's the distance off. So we could say the error is, R is less than 0.033, which means, to be honest, in this problem, since we used R, shouldn't we technically just leave it like that?
But it's alternating, so I have to take into account both sides.
True, but since we called it R, do you know what I mean? R is the absolute value. So we could just go ahead and say like that. And then just understand, hey, that's going to be either above or below. Is that cool?
Question. The alternating series one, what does that tell us? Is that the R? I know that S means, if you do the S, it means you do...
Alternating series error bound, or alternating series error estimation remainder theorem something. I don't remember what the card's called. But with alternating series, we can say that the error of using n terms to approximate a value is going to be less than the n plus first term. So we found the n plus first term, and we said up here, which we were going, which is the type of question that we had seen earlier this year. We were saying, okay, so what range must the sum have? Should the actual value have? And that's when we were taking this value over here, and we were adding him, and we were subtracting him. We were finding the range for the sum itself, and that's what we've done a lot in the past with our alternating series. But this question specifically asked, what is the remainder? What is the error bounded by? And so we've seen from the last card, error is defined to be the difference, the absolute value difference, which means above or below. This is saying from the alternating series remainder theorem that the remainder is definitely less than 0.44366. And from Lagrange, we were able to be even more precise and say, hey, it's definitely less than 0.000333.
So that's just the error range, right? What the error has to be between?
Well, we're not technically showing between because we're not showing the absolute value. If we were to show the absolute value, we're using the remainder like they were saying, like they were defining and saying that it was positive, like its magnitude. But we could say the error, like if you're thinking the positive or negative, the error is between the positive and the negative of those values.
So the remainder which is the error, is less than that.
Dun. Okay, let's go to our worksheet then. So we'll see a little bit more AP-ish of a thing. Example number 1. Struggle at the way hopefully I expected. We might keep going on this tomorrow, but you guys really need to start on the one tonight. Example number 1. Let f be a function with 5 derivatives on the interval 2 to 3. So we know it is at least differentiable 5 times. Assume that the fifth derivative of x is less than 0.2 for all x in the interval. Hey, did they just maximize the fifth derivative for us? Oh. And that a fourth degree theta polynomial, 4f at 2, is used to estimate f of 3. How accurate is this approximation? Give 3 decimal places. Yes, we are using our calculator. What are they asking us to do? How accurate? What does that mean? That means how far off, right? Did they tell us that this is an alternating series? Nope. So what are we using? Lagrange. Just help us remember the name. I'm writing it first. And what does Lagrange say? Remainder. Why am I saying sub 4?
Because it's when we're trying to see how accurate it is.
Yeah, and we're using the fourth degree theta polynomial, right? So n is 4, using the fourth degree. Of 3, why am I plugging in x is 3?
See that.
For estimate.
Yeah. So c is 2, x is 3, right? Is equal to,
How do we know it's not x?
Yeah, that's all I want.
oh, they
Because
told
C
us
is
f
2.
of 3 and they told us c is 2. Sorry, it was hiding down there then. And we know since we're using a fourth degree, then everything's talking about fifth degrees, right?
Yes. So can we just say that it's 0.2 over
Exactly.
Oh, x minus
X minus 2, right? Does that make sense?
Yeah.
And if x equals 3, right? Now, I am going to change something real quick in the last example. You guys know how I said less than because we're choosing z to maximize? Remember how z is allowed to equal the endpoint?
Yeah.
So we're going to say less than or equal to because z could be 0. That's not unheard of. It could be 0 or 0.1 or anything in between for the last example. So we're going to put less than or equal to. What did they tell us about the fifth derivative? It's less than 0.2. all over 5 factorial.
But it's not equal to 0.2.
3 minus 2 is 1, 1 to the 5th is 1.
Yeah, does that make
Good.
a difference?
Now, that's a good question. Hold on. So if this was the maximum value based on these two, and if it was at one of these two, we would be able to say 0.2 within or equal to, right? I wanted to go back and fix the last example. It should have been or equal to. But the problem is, since they said less than, you are correct in this example, since they gave us the information. They just gave us some random bound to use. We are just going to say less than. That is proper. Well, they told us the derivative is for sure less than, so whatever derivative within 2 to 3 is going to have to be less than that. Right?
So are we plugging in 0.2
For the 5th derivative, because that's the highest it could possibly be in the interval 2 to 3. And not even the highest, that's not the highest because it's not or equal to. So we just have to use what they gave us. We know nothing else. We don't know function, we don't know series, we know nothing. Right?
So that's the answer?
Almost. Solve, 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 and this ends up equaling 0.0016. The whole should be in.
Oh, so the part where it's like f5 prime of z over 5 factorial has to be less than 0.0016.
These have 3 decimal places, so we'll round it to 0.002. Remember Lagrange maximizes the error, so the error is going to be less than, or we could just say the maximum error of this approximation is 0.002.
Oh, you're right.
Yeah, it said 3 decimal places, so I figured like I should be precise. Does that make sense? So then letter B, what does it say? Suppose that, hey, who is this guy? Piece of 4 of 3?
That is the
Actual, or the one that you got when you do it.
The 4th degree Taylor polynomial at 3. And it says use this answer and use what you did in A to find an interval in which f of 3 must reside.
That needs to be alternate.
Yeah, we could say a piece of 4.
Why can't we do the alternating series version now?
No, we're not. We're saying that the error or the remainder is the actual minus. That's from our part. Oh, it's up above. The remainder is the actual minus the Taylor, or the Taylor minus the actual. Either way, it's absolute value. The order doesn't matter. Right?
yes.
So we go ahead and plug and chug and then add, and we end up that f of 3 is less than. If you want to be super snazzy, you can just do 1.763 plus 0.002 if you want to stick it to the man. And you could do negative 1.763. I don't need to add it still. Why did I put a negative? Add
Yeah.
1.763 minus 0.002.
Wait, can we stick it to the map?
Yeah, that
I
works.
thought we have to combine it all.
Well, if we have a numerical expression, remember, you can always leave it. But technically, if you want to know what that would end up being, it would end up being that f of 3 is in between.
1.761 and 1.761.
So, question: how would you answer letter C? Could f of 3 be 1.778? No. Why not?
It's not within the air. I don't know how you say that. Oh, it's not within.
the range.
I can't spell within. that make sense? And I just use their wording, the interval. And so what can you say about letter D? Because 1.764 does reside within the acceptable range, the acceptable interval, where f of 3 must reside. Those clocks on keep throwing me off. I'm like 12:31, lunch. Wait, no.
Oh.
Oh, it's 11:30. Oh, never mind. I don't know about the clock. Anyway, so
That's what
Does that make
was saying
sense?
today.
yeah, it's trippy. Book example in our notes.
Miss D,
Actually, hold on, let me see. I'm listening.
if we found out that what R sub 4 of 3 actually was not less than, would we do that f of 3 minus c sub
So I can do plug in L of
equals-
1.1. Is that what you mean? Oh no, wait, but we can't find the actual anything because we don't know the function.
No, I mean like
Theoretically.
yeah, like theoretically.
Okay.
Would it be negative 0.002 equals that equals 0.002? Not less than?
The error can't be multiple things at once.
So
How far off the actual will be from the approximation is one solid number that is in between. That is in the interval. Like how far off the error will be in the interval from negative 0.002. So either 0.002 below or up to 0.002 above. So letter A is answering the absolute value. The absolute value of the max, how far off it can be. And then B is actually applying that and saying, oh, okay, so it could be 0.002 above plus, or 0.002 below minus.
but okay, so if B would be the same if it wasn't less than, like we know for a fact it equals 0.002.
But it's not based on the given up above that says the fifth derivative is less than 0.2.
I mean, theoretically, if it said it equals it, it was.
Oh, you're saying, changing the given.
Yeah,
Okay, then it would be less than or equal to.
less than or equal to.
Yeah, not equal to, but less than or equal to. And greater than or equal to.
Why is that?
Because it's in between. It's in between. Okay, number 34. This is from our book. This is like the latter end of homework. It's given us a little bit different information. Homework's due tomorrow.
Oh.
Fully attentive, but you might get stuck just a little bit.
Do it ladder.
Fully attentive. Ladder. What's ladder?
Because you said later.
Ladder times.
It's like the ladder part of homework.
Mm-hmm.
It's fully attentive mean like I tried it and I didn't get through it, so I quit.
Yeah. Yeah.
That counts.
So you try it and you get as far as you can, and then you come with questions tomorrow as we finish our examples.
This question one count.
34. F of x equals sine of x squared plus cosine of x. The graph of the fifth derivative is shown below.
Yeah,
This might be a non-calculator problem. Alright, the first four non-zero terms in the Taylor series for f about, we're lucky, about x equals 0, which means we can use our special, what?
McLaurin series.
Okay, how are we going to find the first four non-zero terms?
It's odd.
Can you
It's
just,
odd.
can you do them separately and add them together?
Mm-hmm. What would sine of x squared be?
It would be 2 cosine of
One
x squared.
So,
minus
2x cosine.
can we do sine first and then can we just multiply by x?
What are you doing?
Wait, sine is odd, right?
Right.
So
it's
you
gonna
start
be
with x and you plug in
and
the x squared.
Over, okay, yeah, so then x to the 6th over 3 factorial.
And x cubed, x squared cubed would be x to the 6th, good, over 3 factorial.
And x to the 10th.
And then x to the 5th, x squared to the 5th would be x to the 10th over 5 factorial, right?
Yeet.
Wait a minute, what?
And then minus, plugging into the Maclaurin, special Maclaurin series.
Right, right.
And then it's going to be 714 over 7 factorial. X to the 7th.
X squared to the 7th, which would be,
Yay, go easy moves.
oh, hold on, we gotta get rid of this guy, because he's ugly.
Me?
I shouldn't personify things I'm getting rid of, because they're ugly. I don't know what it is. I'm
I'm
erasing my nasty writing to make it better. Okay, so, that's sine of x squared, that's great. Who's cosine of x?
Is even.
Which means?
McLaurin.
McLaurin. Learn.
is x squared over 2 factorial plus x to the 4th. Over. Yeah, there you go.
Gotcha.
Every time you do that, George, it reminds you of that scene from Indiana Jones 3.
Cosine's alternating too, right guys? And that
Yes.
even but alternating, yeah. So what we gotta do? Oh man.
Cosine.
Oh wait, we only need the first 4 non-zero terms.
So that makes add up.
Go team. So then we end up with
2x
the x
squared.
squareds combined, right?
So
So 1x squared plus 2 factorial is just 2, so 1 half, 1 and a half, 3 halves.
what? Oh. What?
Which is why are you adding? Oh, you're adding.
Because I'm adding.
So 2x squared over 2 factorial. So shouldn't that just be x squared?
Oh,
Wait.
no.
Because x squared
1,
plus x
2
squared.
factorial is a half. So 1x squared plus a half x squared is 1 and a half x squared.
I don't know why I'm multiplying. No wait.
Wait.
Because x squared
1x squared
plus x squared
plus a
is
half
2x squared.
plus a half x squared.
No, we can't put
You're
it
doing
over
pen
here.
pass wrong. You're adding then dividing.
Okay.
You divide then add.
Yes, ma'am.
Wow, I really can't do this.
So 1x squared plus a half x squared is what's wrong?
You don't know how to
3
count.
x squared.
I really don't know how to
Aye,
count.
aye, aye. Who would be the next term?
And
I
the
don't want to
6 is-
try.
No,
well,
it's x to the 4th, right?
But the 6 is combined with that. I thought this was.
So that'd be x to the 4th over 4 times 3 times 2 times 1, 24.
For the one of the notes for a cosine.
Oh,
is
what the heck?
That one for.
Oh, stink.
Son of a go.
You guys, we forgot the 1 in front.
What
little
did we
one.
forget? We didn't forget a 1.
Yeah, we did.
Oh, and the cosine? Yeah.
Yeah, we forgot the 1.
Not
Thanks,
the-
Amanda.
I give up.
What happens when I go too quick?
When you get too lit, is that what I just heard?
So that's a minus, and that's a plus, and that's a minus, and that's a plus. That's
Yay! So that means we don't have to combine.
When I say 1 goes first,
The 6s. Oh.
so 1 minus a half would be a half x squared, right?
Yes.
And then we have
X to the 4th.
an x to the 4th.
Over 24. I think that's what you said.
Wait, why is it over 24?
4 times 3 times 2 times 1.
Oh,
Factorial.
no.
And the first 4 non-zero terms. Okay, so we got 1, we got 2, we
Now we're
got
just going to
3.
combine the 6s. And the 6s do not cancel.
Bummer.
So it's negative 2x to the 6th. How do you get the bottom? Again?
3 times 2 times 1 is 1/6. 6 times 5 times 4 times 3 times 2 times 1. 4 times 3 is 24.
That's
24 times 5 is 120. 127. 20. Good.
Times.
So I have
6.
negative 1/3.
Divided by 2. 2, 1, 6, 0 on the bottom.
2, 1, 6.
Sorry, say that again?
2, 1, 6.
I rebuke you in the name of Jesus. It's no longer ugly.
So negative 121.
What?
Wait, I don't know.
Oh, it's like,
Wasn't it?
What the?
That's negative 1/6 minus 1 over 720, right?
Oh,
And I have to get common denominators.
together. I keep multiplying.
So negative 120 minus 1 is negative 121. Guys, I thought you wanted back to numbers,
Six
no?
math plus 4.
what?
It's been so long since we've done numbers.
Okay, letter A. Dun, 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 dun.
Yay, Cosimo.
That was fun. Letter
Fun
B.
life. Ooh. I want to do this. So I attempted homework.
No. Look.
I'm looking.
Yeah,
Value of
that's
the
right.
sixth derivative of 0.
What?
The sixth derivative of f when f is sine x squared plus cosine.
So that's the 5th derivative shown. Can we use that? At 0, it's D&E, because it's a sharp point.
You're looking at the fifth derivative.
Right, so then when you derive it, you won't be able to derive it. Right? No?
I think Sam is.
What?
Alright, I take it.
Why?
Because you plug in
The sixth term is f. The sixth derivative of f at 0 times x to the 6 over 6 factorial. So we have to say, hey, that's x to the 6. Hey, that's 6 factorial. So who's that guy?
Nothing.
The sixth derivative of f.
Oh, that was negative absolute value.
Yeah.
That makes sense.
One to take all.
Randy, you're fucking
Alright, we're trying. Joyce, we're gonna keep going tomorrow. Hopefully not the entire class period on examples with Laurent.
I'm really confused.
Wait, where's the card? Oh, thank you.
Yeah.
If you just